We have 47 days left to study 3IATLAS before it disappears forever, and scientists are running out of answers. Section 1. The ticking clock. Every now and then, science throws you a curveball, a chance to see something wild and rare, maybe once in your life, maybe never again. And just as quickly as it appears, the universe starts to snatch it back. Right now, out past Mars in the deep cold, there's an object from another star system cruising through our solar backyard. Its name, 3IATLAS. It showed up out of nowhere, close enough for us to catch a glimpse, and now it's heading out, the window closing fast. NASA scientists, astronomers across the country, and folks all over the globe are tracking it as it fades away bit by bit each night. They're full of questions, big ones, and the clock is ticking. Before we dive any deeper into this mystery, I just want to say something real quick. Making these documentaries, it's a ton of work. Days spent digging into research, writing scripts, editing, trying to share stories that are both accurate and actually interesting. If you like what I do, if these stories about the unknown get your brain buzzing, I'd really appreciate it if you subscribed or left a like. It's not just about numbers. It tells me this stuff matters, that we're all curious together. Thanks for being here. So, 47 days. That's what some researchers are betting on before 3IATLAS gets too dim and far away to study properly. 47 days to untangle mysteries that don't fit any of our neat boxes. 47 days to figure out why this thing acts so strangely, why it looks the way it does, and what secrets it's trying to share about worlds beyond our sun. This isn't about wild guesses. It's not about hype either. This is about stubborn data, numbers that won't behave, and scientists doing what they always do when the universe throws them a puzzle, asking sharper questions, building new theories, and admitting when something just doesn't add up yet. There's real urgency here. Everyone working on this knows exactly how rare this is. We're not talking about just another space rock. This is a visitor from the darkness between the stars, a messenger carrying clues about places we'll never go, conditions we'll never see for ourselves, and a history that makes human civilization look like a blink. Interstellar objects basically never show up. We've only confirmed 3 ever. The first, 1I/Oumuamua, zipped through in 2017 and left everyone scratching their heads with its weird acceleration and complete lack of a visible tail. The second, 2I/Borisov, came in 2019 and acted more like a normal comet, finally, something that made sense. For a moment, it felt like the cosmos wasn't just messing with us. Now comes 3IATLAS. This one's a trickster on the surface. It looks like a regular comet, but when you dig in, it does things that shouldn't be possible. It fits our models just enough to seem familiar, but then breaks the rules in ways that make scientists uneasy. Astronomers have seen plenty of strange things. Comets that shatter unexpectedly, asteroids with hidden ice, far-off objects with orbits that hint at something big tugging on them from the dark. But those all came from our own solar system. We can at least guess how they formed, shaped by the same mess of dust and gas that built our planets. 3IATLAS, totally different story. This thing was born somewhere else, different star, different system, probably under conditions we can only imagine. It's been drifting through the emptiness between stars for who knows how long, taking hits from cosmic rays and micrometeoroids, frozen solid in the deep dark. So by the time it reached us, it wasn't some untouched relic. It was a survivor. A traveler, changed by its journey in ways we're only starting to figure out. Now, as it passes through this one window where we can actually get a good look, our instruments are picking up things that don't make sense. Weird enough that even the most hard-nosed scientists have to stop and wonder if we're missing something big. That looming deadline makes everything feel more intense. Usually, if you spot something odd in your data, you've got time. Time to double-check, time for more observations, time to tweak your models and try new ideas. You can be patient. Let the truth shake itself out. With 3IATLAS, patience isn't really an option. This thing is on the move fast. It's fatting, slipping away at several kilometers per second, and once it drops below the sensitivity of our instruments, that's it. The show's over. Any questions we haven't answered by then just hang there in the dark, maybe forever. The odds of another interstellar visitor showing up at just the right moment, in just the right spot, and shining bright enough for us to study. Honestly, they're tiny. We got a wild stroke of luck with Oumuamua, caught a break again with Borisov, and now somehow a third time with 3IATLAS. A fourth shot. That could be decades away, maybe longer. So when astronomers say they've got 47 days, they mean it. That's not drama, it's math. 47 days before the signal-to-noise ratio sinks, before the photon count gets too low for spectroscopy, before the orbit data gets so fuzzy we can't pin it down anymore. Then the window slams shut and we're left with whatever we manage to grab, whether it's enough or not. Before we dive deeper, let me just say why I spend so much time on stories like this. I make sleep documentaries about cosmic mysteries, like 3IATLAS, hovering on the edge of what we know and what we're still trying to figure out. I'm not here to freak you out or chase clicks. I want to share real science, actual data, and the honest questions that keep astronomers up at night. The way I tell these stories is a choice. Calm, unhurried, with respect for both the facts and the mystery. I want to inform you, spark a little wonder, and maybe give you something peaceful to fall asleep to, something bigger than everyday worries. If that sounds good to you, if you like wandering down these astronomical rabbit holes, I'd love for you to subscribe. Tap the like button. Say something in the comments, share your thoughts, your questions, what makes you curious about the universe. These videos take a huge amount of time to research and put together, and every bit of support helps keep them coming. And honestly, there's no shortage of cosmic mysteries. The universe keeps throwing curveballs. So let's get back to what's actually going on out there, right now, as 3IATLAS glides through our little corner of space. Like a lot of big discoveries in astronomy, this one started with something totally ordinary. A telescope sweeping the sky. A computer algorithm flagging a moving blip. A researcher glancing at the data, probably thinking it's just another comet, another chunk of ice and rock circling the sun. But this one didn't fit the pattern. It was doing its own thing. At first, the difference was barely noticeable, but it turned out to matter a lot. 3IATLAS showed up on July 1st, 2025, thanks to the Atlas Survey Network. That's a set of robotic telescopes built to watch for asteroids, comets, and anything else shifting against the backdrop of stars. Atlas operates out of Hawaii, with NASA and the University of Hawaii teaming up to run the show. It's an American-led effort, part of the bigger mission to track near-Earth objects and figure out what's moving through our neighborhood. Atlas is a special kind of clever. Instead of staring at one target for hours, it sweeps the whole sky it can reach, night after night, looking for anything that changes. It's like a solar system security camera, always on the lookout for surprises. There are 4 Atlas telescopes, 2 in Hawaii, 1 in Chile, 1 in South Africa. Each one snaps hundreds of images every night. Then the software compares these shots to older ones, looking for new dots of light, shifts, or changes in brightness. Most of what it finds are familiar. Asteroids and comets we already know, cruising along as expected. But every once in a while, it catches something no one's seen before. That's how it started on July 1st, 2025. Up on Mauna Loa in Hawaii, nearly 3,400 meters above sea level, the Atlas telescope caught something odd, a faint smear in the night sky. Out there, the air's thin, the sky's dark, and you can see just about everything. The detection popped up automatically. No one saw it with their own eyes at first. All the software did was spit out a line. New moving object detected. Requires follow-up. Within hours, the alert zipped over to the Minor Planet Center at the Harvard-Smithsonian in Cambridge. That's the place where observations of small solar system bodies pile up. When any observatory on Earth finds a new asteroid or comet, the data heads straight to the MPC. The team there collects observations from all over, runs the numbers, and figures out if they've got something new or just a familiar object taking a weird route. At first, 3IATLAS didn't look like anything special, just another blurry spot, a moving dot. Astronomers see dozens of them every night. The early brightness readings pointed to something maybe a few hundred meters, maybe a couple kilometers wide. Its slow crawl against the stars said outer solar system. Nothing strange. Not yet. But then the MPC started crunching the orbit. Right away, the numbers looked off. The speed was a little too high. The path didn't bend the way it should if the sun was keeping it in check. They double-checked, folding in new data from other telescopes. Pan-SDARRS in Hawaii had it. Catalina Sky Survey in Arizona caught it too. With all these views from different spots, the orbit came into focus. And the clearer it got, the more unsettling it seemed. The orbit was hyperbolic. That changes everything. If you've got an elliptical orbit, the object's stuck circling the sun. Parabolic means it just barely escapes the sun's pull. But hyperbolic, that means it's got extra energy. It's not coming back. It's just passing through, one shot, then gone, out into the spaces between the stars. That made 3IATLAS only the third confirmed interstellar object we've ever found. The first was Oumuamua in 2017. That long, strange visitor that sped up in ways gravity couldn't quite explain and got people wondering if it was natural at all. Second was 2I/Borisov in 2019, which behaved just like a normal comet and settled everyone's nerves. Now we had a third, 3IATLAS. The big question, was it going to be weird or was it going to be normal? At first, it looked normal enough. Early spectra from Gemini and Keck, both in Hawaii, showed all the usual comet stuff. Water vapor, carbon dioxide, carbon monoxide, dust. You could see the coma, a fuzzy cloud of gas and dust boiling off the surface as it got closer to the sun. It even started growing a tail. Scientists let themselves relax a little. Another interstellar comet like Borisov. Odd because of where it came from, but still following the rules. The physics checked out. The chemistry checked out. Everything clicked. But that relief didn't hold up. As better data came in, as more powerful instruments got a look, little inconsistencies started popping up. Nothing big at first, tiny things you could maybe brush aside, but the cracks were there. Oumuamua was weird because of what it didn't do. When Pan-SDARRS in Hawaii first spotted it in October 2017, astronomers thought comet or asteroid easy, but it wasn't either. No coma, no tail, no signs of outgassing, the stuff comets do when they get near the sun. It looked like a bare, tumbling rock. But then it did something rocks aren't supposed to do. It sped up. Not by much, but enough to notice. As it swung around the sun and headed back toward the void, it left just a little faster than gravity alone could explain. The acceleration was tiny but real, and no one could quite pin down why. Cometary outgassing can easily cause that kind of acceleration. When jets of gas shoot out from a comet's surface, they act like little rocket thrusters, pushing the whole thing along in ways we can predict. But with Oumuamua, nothing like that showed up. No shimmering cloud, no dust, nothing. Even with our best spectroscopes, we saw no trace of gas. It just kept speeding up, and for all we could see, there was no reason at all. Scientists scrambled for answers. Maybe Oumuamua was made of weird ices, hydrogen, nitrogen, stuff that could evaporate without leaving a visible trace. Or maybe that bizarre, stretched-out shape, the one we pieced together from how its brightness changed as it tumbled, somehow gave it extra thrust. Some thought perhaps it was just fluffy and light, pushed harder by sunlight than other things we'd seen. And then there was the idea that just wouldn't go away. What if Oumuamua wasn't natural? What if it was something built, not born? A light sail, maybe, designed to ride the pressure of sunlight. Or maybe it was junk, the scraps of some alien craft, or even a probe sent by another civilization to peek in on us as it drifted through our solar system. Dr. Avi Loeb from Harvard didn't just whisper this idea. He said it out loud. He argued that the acceleration, the odd shape, the total lack of comet-like features, all pointed to something technological. Lots of astronomers pushed back hard. They said if you want to make a claim that wild, you need proof, and all anyone had was circumstantial. People argued about it for years. Some still do. By the time Oumuamua left the solar system in 2018, fading from our view forever, we were no closer to an answer. It's out there now, beyond our reach, carrying its secrets with it. Odds are, we'll never know what it really was. Then in August 2019, along came 2I/Borisov. Gennady Borisov, an amateur astronomer in Crimea with a homemade telescope, spotted it. Borisov was the opposite of Oumuamua. It was normal, almost boringly so. It had a bright coma, exactly what you'd expect. It sprouted a tail of dust. When scientists pointed their biggest telescopes at it, including Hubble, they found water vapor, carbon monoxide, all the usual comet stuff. It looked like any other comet we'd seen, just one that happened to wander in from the stars. Everyone pounced on Borisov. Hubble snapped pictures over and over. ALMA in Chile picked up molecules in its wake. Observatories in the US and Europe joined in. All the data lined up. Borisov was a comet through and through. The only odd thing was where it came from. People breathed easier. Maybe interstellar objects could be normal after all. Oumuamua was just a fluke, the weird one. Borisov set the standard. But then in 2025, 3IATLAS showed up. And it's not making things easy. It looks like a comet, sure. There's a coma, there's gas jetting out. But the composition, off. The behavior, off. The numbers don't settle down the way they should. It's close enough to normal that you want to believe it, but nothing quite fits. 3IATLAS reached its closest point to the Sun, perihelion, on October 30th, 2025. That was supposed to be the big moment. The Sun would heat it up, drive out gas, make it shine, maybe even spark some surprises. But bad timing. From Earth, the comet was lost behind the Sun at just the wrong time. For days, we couldn't see or track it. And when it finally emerged, something was different. It had changed course. Not by much, but enough that we noticed. Scientists call this a non-gravitational acceleration, a nudge that gravity alone can't explain. Usually for comets, that's just outgassing again. Jets of gas shoot off, the comet gets pushed a little. But this time, the details don't add up. The size of the push when it happened and which way it went, none of it quite matches our expectations. Was it normal comet business? Or did something else happen while it was hidden behind the Sun? At NASA's Jet Propulsion Lab in Pasadena, the team keeps tweaking the orbital path of 3IATLAS every single day. Each fresh set of telescope data, whether it's from the US or halfway across the globe, feeds into their models. And here's the thing. More data means a sharper trajectory, sure, but also more weird little details that don't quite fit. Lowell Observatory in Arizona, Palomar in California, and McDonald in Texas have all pitched in. Even the big guns in space, Hubble and James Webb, have zeroed in on it. Out closer to the Sun, NASA's Starry and the ESA NASA SOHO spacecraft have managed to catch it sneaking by. So with all this data, you'd think we'd have a clear picture. On the surface, it's a comet. Easy, right? But the deeper you go, the messier it gets. First, the nucleus. No one can agree on its size. Some put it at 440 meters. Others say it's nearly 6 kilometers across. That's not a small difference. Why is it so hard? Because the nucleus is hiding inside a cloud of gas and dust, the coma. We can't separate the solid core from all that haze, especially from this far away. Any measurement of brightness is really just a messy mix of the core and the coma. If you change your guess about how reflective the surface is, or what the dust is made of, or how active the outgassing is, the size estimate swings wildly. The chemistry is just as strange. James Webb's infrared eyes spotted something weird. The coma is loaded with carbon dioxide, not water. That's rare. Most comets in our solar system use water ice as their main fuel. Sun hits the water ice, it boils off, and you get that familiar tail. But for 3IATLAS, carbon dioxide's doing the heavy lifting. The CO2 to water ratio is off the charts. Almost no comet we know has numbers like this. It all points to one thing. 3IATLAS didn't form around our Sun. It started somewhere else, around a star where carbon dioxide was way more common than water. So, it doesn't just look different, it really is different. It's a visitor, carrying the chemical signature of a place we'll never see. Then you've got the ultraviolet data. Even when it was way out, more than 3 times the distance between Earth and the Sun, a place where most comets are pretty much dead, 3IATLAS was still throwing off water vapor. The instruments picked up hydroxyl emissions, which only show up when sunlight breaks apart water molecules. That kind of activity, that far out, is weird. Maybe the ice in 3IATLAS turns to vapor at lower temperatures, or maybe its structure is just bizarre. Something about it keeps it active when other comets would be asleep. And then there's the photo that set everything on fire. Early November 2025, an amateur astronomer, Paul Craigs, snaps a shot with a Dwarf 3 telescope. The image is nothing like what Hubble or the pros have shown. Instead of a fuzzy blob, you see a sharp-edged object blazing white core with this smooth blue halo, almost like an energy field. The internet lost it. Amateur astronomy forums blew up. Some people called it overcooked. Others blamed glitches or bad software. But then the copies started rolling in, other amateurs, similar gear, posting their own images. And they all showed something structured, almost too perfect, too clean for a natural comet. The pros jumped in to cool things off. Artifacts happen. Stack enough exposures and you get fake details. Cheap telescopes are good, but they're not Hubble. They miss things. They add noise. But the question stuck around. What if the big professional telescopes, so finely tuned to spot fuzzy comets, are actually smoothing out details that backyard astronomers are catching? What if there's more to 3IATLAS than the official images let on? NASA scientists, along with teams at other institutions, are pretty careful when they talk in public. They stick to the facts. Everything we've seen so far says 3IATLAS is just a natural comet. No weird radio signals. No strange heat coming off it. No shapes or features that comet physics can't explain. The jets, the coma, the tail, it all checks out, even if it's pushing the boundaries of what we usually see. But behind the scenes, at conference coffee breaks, in long email threads, the mood shifts. There's a mix of excitement and irritation. The data just keeps throwing curveballs. Take the polarization measurements. Polarimetry is all about how light scatters and becomes polarized when it bounces off stuff like dust or ice. Normally, by looking at the polarization, scientists can figure out things like particle size, shape, and what they're made of. But with 3IATLAS, things got weird. Before it even rounded the sun, a team measured its polarimetric properties and found something nobody had ever seen. The negative polarization branch, a feature every comet or asteroid shows, was deeper and narrower than anything on record. Polarization hit about -2.7% at small angles, with the inversion at 17 degrees. To put it simply, the way light bounces off this thing doesn't fit any known comet or asteroid. It's weird. It's in its own category. So what's up with that? Maybe the dust grains are unusually tiny or have some strange shape. Maybe the surface has a texture or mix of stuff that scatters light in a totally different way. Or maybe, after drifting through interstellar space for millions of years, cosmic radiation has cooked the outer layer, changing how it reflects light in ways we just don't see with our local comets. That last idea is picking up steam. There's a solid theory, newish, but based in real physics, that interstellar objects get blasted by cosmic rays for eons. High-energy particles slam into the surface, breaking chemical bonds and splicing molecules together in new ways. Over time, this bombardment creates a process crust, a weird skin nothing like the fresh ice the object started with. Carbon monoxide turns into carbon dioxide. Organic molecules get built. Water ice gets altered or even destroyed. By the time something like 3IATLAS reaches our solar system, its outside might be completely transformed. If that's what's happening here, then all this oddness, the carbon dioxide, the strange light polarization, the high activity, could be because of the journey, not where it originally came from. We're not seeing a perfect sample from another star system. We're seeing a traveler that's been changed, maybe even battered by the trip. Even so, there are still big gaps. If radiation has really weakened the outer crust, why hasn't 3IATLAS broken apart? Comets are fragile. They fall to pieces all the time, especially when they swing close to the sun and heat up fast. Yet 3IATLAS is still holding together. That could mean its core is tougher than we thought, or maybe something about its insides gives it extra strength. Then again, some researchers are starting to ask if maybe it's just not built the way we expect at all. And now, the clock's ticking. 47 days left, give or take, depending on which telescope you ask. After that, 3IATLAS fades into the background, too dim for all but the biggest telescopes. The window slams shut. If we haven't figured things out by then, we might never get another shot. Who knows when the next interstellar object will show up? could be decades. Maybe the next one will be too faint to spot or pass through a part of the sky we can't see. This is it. This is the moment. And it's slipping through our fingers. So scientists are scrambling. Teams everywhere are coordinating their observations across every wavelength they can. Optical telescopes are watching for changes in brightness and shape. Infrared instruments are sniffing out the chemistry of gases and ices. Ultraviolet detectors are picking up signals from water and other stuff boiling off. Radio telescopes are tuned in, just in case there's anything odd to hear, even though so far there's nothing but silence. Every night, as 3IATLAS moves farther from the sun and farther from Earth, it gets a little dimmer. Every night, the signal-to-noise ratio drops a little more. Every night, the chance to catch something unexpected, something that might rewrite our understanding of interstellar objects, diminishes. And every night, astronomers at observatories across the United States and around the world point their instruments at a fading dot of light and hope that tonight will be the night the data finally makes sense. Because right now it doesn't. Section 2. When discovery feels routine. Modern astronomy has its own rhythm, and honestly, most people never see it. Forget the old story of a lone genius under the stars making history with a single eureka moment. That's a great tale, but it belongs to a different time, back when someone with a telescope and a hand-drawn chart could actually change what we know about the universe. Things have changed. Astronomy today runs on teamwork, technology, and systems. It's more methodical, more collaborative. And there's a certain beauty in that, watching understanding grow bit by bit through steady, patient work. Think of it less like a group of isolated geniuses and more like a massive, finely tuned machine. Telescopes, detectors, computers, and experts all over the world, everyone and everything working together to catch faint signals from distant corners of space. This is big science for real. It takes coordination across countries, institutions, and time zones. Take the discovery of 3IATLAS. No single person spotted it, no flash of inspiration. It was the system, the network, doing exactly what it was built to do, finding the unexpected before it slips away. Most telescopes have their nights planned months ahead. Observing time is a hot commodity, and researchers from everywhere send in proposals, hopping for a few precious hours to chase their questions. Committees sift through stacks of requests, weighing which projects matter most, who gets a shot and who waits. Some get a quick look, others lock in years of monitoring. But survey telescopes like Atlas don't play by those rules. They don't wait for requests or cherry-pick targets. Instead, they sweep the sky over and over night after night, looking for anything new or odd that pops up. A blip, a movement, a sudden flash where there was nothing yesterday. The data never stops. Every night, hundreds of gigabytes pour in. Millions of images, billions of stars and galaxies and other stuff. No one could look at all this by hand. It'd take lifetimes, so the computers take over. Complex algorithms scan new images, compare them to old ones, and flag anything that stands out. A new dot of light, a moved object, a star that's flickered up or down. Most of these are false alarms, cosmic rays, technical glitches, ordinary stars doing their usual thing. But sometimes the system catches something real. Sometimes it matters. When Atlas flagged 3IATLAS on July 1, 2025, it was just following its usual routine. Snap a picture, process it. Compare, spot a difference. Send an alert. No drama, no cheers, just another blip in a growing database, waiting for someone to check it out. That alert zipped off to the Minor Planet Center at the Harvard-Smithsonian in Cambridge, Massachusetts. The MPC has been the global headquarters for tracking small objects in the solar system since 1947. Back then, they used telegrams and snail mail. Now, they get thousands of reports daily from all over the world. The MPC team, a handful of astronomers and computer scientists, sorts through this avalanche of data. They collect observations, make sure each detection is real, work out rough orbits, and figure out if something's truly new or just a rediscovery of a lost object. Most of it is routine. An observatory sends in a new asteroid. The MPC checks its files, already known, orbit updated, move on. Another report shows up. This one looks new, but they need more data to be sure. They send out an alert. If you've got time, take a look at this one. Every so often, the data throws you a curveball. Something pops up that just doesn't fit, something weird enough to make you double-check the numbers and wonder if you've made a mistake. That's exactly what happened with 3IATLAS. The first orbit calculations came back, and surprise, they showed a hyperbolic trajectory. Whoever crunched those numbers probably stared at the screen for a second, maybe thought, "That can't be right," and then ran the whole thing again. Hyperbolic orbits aren't just rare. They're almost unheard of unless you're looking at something moving fast enough to escape the sun's gravity entirely. Regular solar system stuff just doesn't do that, but interstellar objects do. These are wanderers, flung out from other star systems, drifting through the galaxy for ages before finally stumbling across our little patch of space. We'd seen two before, Oumuamua and Borisov. Now it looked like we had a third on our hands. This wasn't something you sit on. The news needed to get out fast. Within hours, the International Astronomical Union's Central Bureau for Astronomical Telegrams, another one of those Cambridge, Massachusetts outfits, sent out a circular. Dry, clinical, packed with numbers, just like they always are. Object 2025 XX1, later designated 3IATLAS, was discovered on UT 2025 July 1.3 by Atlas MLO. Preliminary orbital elements suggest a hyperbolic trajectory with eccentricity approximately 1.2. Further observations urgently requested to confirm interstellar origin. But every astronomer reading that knew what it really meant. Whatever you're doing, drop it. Look at this. Now. And that's what happened. People shuffled their observing schedules. Target of opportunity requests started flying in. Those urgent pleas for telescope time when something big suddenly happens. Telescopes all over the world swung around to the coordinates in the circular. This is how science moves when something rare comes along. The whole community shifts gears. Projects get paused. Long-term plans get thrown out the window. Grad students who thought they'd be working on something completely different suddenly find themselves hunting for interstellar visitors. Nobody wants to miss out, because these objects don't wait around for you. ATLAS, which stands for Asteroid Terrestrial Impact Last Alert System, isn't actually set up to look for interstellar objects. Its main job is planetary defense, finding and tracking asteroids and comets that could threaten Earth. There are 4 telescopes, 2 in Hawaii, 1 in Chile, and 1 in South Africa. Each one scans the sky every night over and over. Every telescope takes hundreds of images, checking for anything new or moving. The system is tuned to spot stuff near Earth, but it doesn't discriminate. If something's moving, it gets flagged, whether it's a typical near-Earth object, something from way out in the solar system, or every once in a while, something from much farther away. 3IATLAS showed up in the data on July 1, 2025, flagged as a possible comet. One of the Hawaii telescopes caught it, and the discovery was a joint effort between NASA and the University of Hawaii's Institute for Astronomy. The initial observations went straight to the Minor Planet Center, the global headquarters for tracking asteroids, comets, and other small bodies. The researchers at the Minor Planet Center, also in Cambridge, ran their calculations. They've got some advanced software for this. Give them a handful of observations and they'll work out where something's been and where it's headed. Normally, these orbits come out as ellipses or parabolas, typical solar system stuff, bound to the sun, following the usual rules. But this time, the math came back different. The orbit was hyperbolic. The object was moving too fast to stick around. It wasn't going to circle the sun, just pass through and keep going. The numbers pointed to an origin outside the solar system, interstellar. That's when everything kicked into high gear. Word got out fast in the astronomy world. An interstellar object, just the third one ever confirmed. Suddenly, observatories scrambled to change their plans. Proposals that had been waiting in line for months got pushed aside so everyone could point their telescopes at 3IATLAS. That's how science works when something rare shows up. The whole community turns on a dime. NASA's Near-Earth Object Observations Program, based at the Jet Propulsion Lab in Pasadena, took the lead on follow-up. JPL is the go-to place for tracking anything that moves out there. Tiny asteroids, distant comets, even visitors from other star systems. They've got the software, the know-how, and the network to rally telescopes all over the world. Within days, some of the biggest instruments on the planet were watching 3IATLAS. The Hubble Space Telescope, run by both NASA and the European Space Agency, aimed its cameras at the object. Hubble spotted a faint coma and the start of a tail, clear signs 3IATLAS was outgassing as it warmed up in the sun. That's what everyone expected. Nothing weird there. Honestly, it was a relief. Then the James Webb Space Telescope joined in. Webb's built to peer through dust and gas, picking up thermal fingerprints that regular telescopes can't see. The data from Webb turned out to be vital, showing 3IATLAS was loaded with carbon dioxide, a bit unusual for a comet. Ground-based telescopes got in on the action, too. The Lowell Observatory in Arizona, famous for spotting Pluto back in 1930, started tracking 3IATLAS, snapping images and collecting spectra to figure out what it was made of and how active it was. Over in California, the Palomar Observatory, home of the historic 200-inch Hale telescope, contributed as well. Palomar's all about time-domain astronomy, watching things that change. And 3IATLAS was changing. Its brightness kept shifting, its coma was evolving. Every tweak was another clue. In Texas, the McDonald Observatory, run by the University of Texas at Austin, joined the hunt. Their telescopes use high-resolution spectrographs to split the comet's light into all its wavelengths, laying bare the chemical fingerprints hiding in the coma's gas. All this data streamed back to JPL, the Minor Planet Center, and research teams at universities everywhere. Every new observation sharpened the picture, nailing down the orbit, the size, the makeup. Piece by piece, the puzzle got a little clearer. For a few weeks, everything seemed almost boringly normal. 3IATLAS acted like a comet. It had a coma, a tail, and the expected signs of water vapor, carbon dioxide, and carbon monoxide. Sure, the orbit was hyperbolic, but that was the only thing truly odd about it. Otherwise, it just fit the comet mold. Scientists started writing papers. More observation proposals went in. People built models to predict what would happen as 3IATLAS got closer to the sun. The general idea was simple. It'd hit perihelion, brighten up as the sun kicked off more outgassing, then fade away as it drifted back toward interstellar space. Clean story, predictable arc, but then perihelion came and we lost it. Nobody messed up. It was just bad luck with the geometry. On October 30th, 2025, 3IATLAS swung closest to the sun, about 1.4 times the Earth-Sun distance, but from Earth's point of view, it was hidden behind the sun. We couldn't see it. Radio signals got drowned out by solar noise. Optical telescopes were totally blinded. Astronomers call this blackout solar conjunction. It hits any time an object slips behind the sun from where we stand. You can prepare, you can schedule before and after, but when conjunction happens, you're flying blind. For 3IATLAS, the blackout lasted anywhere from 40 to 60 hours, depending on the instrument and how close it could peer to the sun's glare. Not the longest conjunction ever, but long enough to lose track. When 3IATLAS finally reappeared, something was off. The brightness had changed. Not by a huge amount, but enough to notice. The coma looked a little lopsided in some images, like jets of gas were firing more on one side. Most telling of all, its path had shifted. Before perihelion, the orbital math lined up perfectly. Afterward, things stopped adding up. 3IATLAS had sped up, but gravity alone couldn't explain it. Something else gave it a shove. Honestly, for comet scientists, that's nothing strange. Comets almost always get a little kick when their ice heats up and turns straight into gas. The gas shoots out and the comet gets pushed the other way like a slow-motion rocket. That's the classic rocket effect, and everyone in the field gets it. But with 3IATLAS, the details weren't routine. The size and direction of the push had people talking. The JPL team took another look at the numbers, plugging in new observations from after perihelion. Their updated models showed 3IATLAS had been nudged just so. Its path tightened, and its speed ticked up. The direction of the push matched what you'd expect from a patch of the comet venting gas, but the timing was odd. All this happened during the blackout, the stretch when the comet was hidden behind the sun and out of sight. Coincidence? Probably. Perihelion is when comets go wild, and perihelion lines up with conjunction just because of how orbits work. The sun blocks our view right when the comet's closest and most active. No big mystery there. Still, that means we missed the main event. No one saw what 3IATLAS was doing at its wildest, when outgassing should have peaked, when anything weird would have stood out. That missing data leaves a shadow of doubt. Some scientists are sure there's nothing more to the story. The comet hit perihelion, blasted out jets, veered off its old path, then settled down as it pulled away from the sun. Textbook stuff, but not everyone buys it. The acceleration was big, maybe too big for the level of activity they saw before and after conjunction. The coma looked busy, but not enough to explain such a focused, powerful kick. Plus, the direction of the burst was so clean, so lined up with the comet's outbound path, that it raised eyebrows. Nobody saying it's aliens. They're just pointing out that the usual story doesn't quite fit the facts. Meanwhile, amateur astronomers were picking up things the pros weren't highlighting. Paul Craigs, for example, snapped a photo with a Dwarf 3 telescope in early November 2025. His shot didn't look anything like the fuzzy coma in Hubble's images. Other amateurs using similar gear saw the same sort of thing: a sharp, almost tube-shaped core, a blue glow, and a tail that looked more like a jet than a cloud of dust. The professionals chalked it up to artifacts. Amateur scopes aren't as precise, and their image stacking can fake details. Odd color balance can make a normal coma look bizarre. That's all true. Still, you have to wonder, are we so sure of our models that we're ignoring what doesn't fit? Things got more interesting with the polarimetric study. When researchers looked at how 3IATLAS scattered light, the results were off the charts, literally. Its polarization didn't match any comet or asteroid on record. The negative branch was something new. The inversion angle was outside anything expected. Clearly, something about the surface or coma was playing tricks with the light in a way nobody had seen before. One idea is that cosmic rays did it. If 3IATLAS spent millions of years out between the stars, it would have been battered by high-energy particles, changing its chemistry and surface. That could explain the weird light signature, the Co-2 heavy composition, maybe even why the structure stayed so stable. But that's just a theory. It doesn't answer everything. By late November 2025, as 3IATLAS drifted farther away, the science community found itself in a strange spot. On paper, the comet model still held up. Nothing about 3IATLAS demanded a wild explanation. Yet at the same time, it was right at the edge of what counts as normal, pushing boundaries from every direction. And the window was closing fast. The comet was fatting. Good data was harder to get every day, and the questions kept piling up. This is the reality of observational astronomy. Sometimes you get clean data and clear answers. Sometimes you get messy data and provisional hypotheses. And sometimes you get an object that refuses to fit neatly into any category, leaving you with more questions than you started with. As December began, researchers at observatories across the United States were coordinating one final push. They had weeks, maybe a month or two at most, to extract every bit of information they could from 3IATLAS before it became too faint for detailed study. The expectation was that routine observations would continue. The comet would fade. The data would be analyzed. Papers would be published. And eventually, 3IATLAS would join 1I/Oumuamua and 2I/Borisov in the small but growing catalog of interstellar visitors. Routine, predictable, normal. But then the data started doing something it wasn't supposed to do. Section 3. When the MEASURMNTS refused to settle. Science has a way of keeping you in check. Just when you start to feel like you've got things figured out, when the data fits the model and predictions line up with what you see, the universe throws you a curveball. Nothing big or dramatic, just enough to make you stop and wonder if you're really seeing what you think you're seeing. Are you measuring the right thing? Did you ask the right question? That's exactly where 3IATLAS lands, right in that uneasy space between I get it and wait, do I? There's this specific kind of frustration that creeps in when your data acts up. It's not outright panic, at least not at first. It starts with a nagging sense that something's off. You run the analysis. The numbers look wrong, so you double-check your code. You go over your calibrations. You try a different way of reducing the data. Still, the numbers just don't add up. Or worse, they're almost right, close enough to tease you but not quite there. When you see numbers that are totally off, at least you know you made a mistake. Maybe you flipped a sign somewhere or messed up a unit. Find the fix, and everything snaps back into place. But when the numbers are just a little bit off, always a bit above or below what you expect, or showing patterns that shouldn't be there, then you start to question if the problem is bigger than your analysis. Maybe it's the model that's cracked. Maybe you're not even looking at what you think you're looking at. By December 2025, the 3IATLAS team had months of data behind them. They'd nailed down the comet's orbit, tightening it with every new observation. Instruments across the spectrum had measured the coma's makeup. The nucleus size wasn't pinned down exactly, thanks to all the gas and dust clouding things up, but they'd boxed it into a reasonable guess. On the surface, things looked solid. They understood 3IATLAS. It was a comet. Sure, an oddball from another star system with some weird chemistry, but still, ice, rock, gas, dust. The physics checked out, but the numbers wouldn't settle. Tiny mismatches kept popping up. Each one alone was easy to brush off, a calibration here, a stray reading there. But together, they started to spell a bigger problem that was harder and harder to shrug away. It started with the brightness data, the bread and butter of astronomy. How much light does this thing give off? For comets, brightness usually follows a simple rule: get closer to the sun, get brighter. Solar heat hits, more ice turns to gas, more dust gets kicked up, and the whole thing shines. Move away, cool down, dim out. There's a power law for this stuff, and while each comet might bend the rule a bit, the pattern holds. 3IATLAS stuck to the pattern until suddenly it didn't. In the middle of November, about 2 weeks after it zipped closest to the sun, the staff at Lowell Observatory in Arizona picked up something strange. Their measurements showed the comet shining just a bit brighter than it should have, given its distance. Not wildly brighter, it wasn't headline news, but it was a real, repeatable difference, a few tenths of a magnitude. You'd need careful measurements to notice, but once it's there, you can't unsee it. Everyone's first guess: delayed outburst. Sometimes comets suddenly flare up when hidden pockets of ice inside them get exposed and start to sublimate. Sunlight takes its time reaching these buried stores, but when it does, you get a burst of activity and a spike in brightness. Astronomers have seen this plenty of times. It fits. So they waited for the outburst to fade. Night after night, they checked the brightness. But the comet didn't dim. Week after week, 3IATLAS kept shining just a bit brighter than the models predicted. Not by a lot, and not enough to blow up the whole comet theory, but just enough to stay stubbornly, persistently wrong, and nobody could quite say why. The team at McDonald Observatory in Texas jumped in with spectroscopic observations, hopping to figure out which gases were making the comet look brighter than usual. If this was some kind of outburst, they expected to see stronger emission lines from water, carbon dioxide, or other volatiles. But the spectra didn't show anything out of the ordinary. The gas mix was the same as before. And when they measured how much gas and dust filled the coma, it matched the numbers from before the supposed outburst. So what was causing the extra brightness? One idea: maybe the nucleus was just more reflective than people thought. If the surface bounced back more sunlight, had a higher albedo, the comet would look brighter. But earlier observations taken before the comet got close to the sun had already pinned down the albedo pretty tightly. That explanation didn't fit. Maybe the coma was denser than expected, scattering more sunlight even if the comet wasn't releasing extra gas. But again, the spectrum didn't back that up. Everything looked normal. The brightness anomaly was small, so most researchers shrugged and chalked it up to a calibration hiccup. Probably just a quirk in the data or something weird in the way the numbers got processed. Nothing to lose sleep over. Still, people noticed. Then the morphology question showed up. Comet comas are usually lively, shifting shapes as the nucleus spins, as sunlight hits new patches, as jets of gas flick on and off. This is normal, and honestly, it's part of why comets are fun to study. But 3IATLAS's coma wasn't playing by the usual rules. It was weirdly stable. Images from Hubble taken over several weeks showed a coma that was almost perfectly circular, with gas and dust evenly spread all around the nucleus. No obvious jets, no plumes, nothing shooting off from any specific spot. That's not normal. Most comets show at least some lopsidedness. The nucleus is usually bumpy and irregular, and as it spins and sunlight hits different parts, you get hot spots where ices vaporize faster. That creates jets, and those jets carve out structure in the coma. 3IATLAS didn't show that, or at least not in any clear way. Some scientists said maybe it was just the angle. Maybe we were looking almost straight down the comet's spin axis, so the jets pointed right at us, making everything look evenly spread. That's possible. It's a known trick of perspective. But honestly, it felt a little too convenient. Stack up enough convenient explanations, and you have to wonder if you're actually solving the puzzle or just finding ways to ignore it. The polarimetric data, though, was the real outlier. A follow-up, this time using ground-based telescopes in the US, backed up the earlier results. The negative polarization branch was real. It wasn't a glitch. It held steady even as 3IATLAS drifted farther from the sun. Usually, a comet's polarization changes as its activity ramps up or down. The dust grains in the coma chain. Size, composition, all that, and so does the way they scatter light. You can actually track those shifts to see what's happening on the surface, figure out which ices are vaporizing, and watch the coma evolve. But 3IATLAS's polarization didn't budge. It just stayed locked, as if the dust grains weren't changing at all, or the process making them was stuck in one mode. Cosmic ray processing could explain it. Maybe, during its long trip through interstellar space, the outer crust of the nucleus got hammered by radiation, changing the dust so that everything released now has the same makeup and structure. That would keep the polarization steady. But that idea opens up new questions. How thick is the processed layer? Are we talking centimeters or hundreds of meters? If the comet was eroding and exposing fresh, untouched material underneath, you'd expect the polarization to shift once clean ice started to sublimate. But nothing changed. Maybe erosion was just slower than everyone thought. Maybe the processed layer was much thicker than any model guessed. Or maybe there isn't any pristine interior left. Maybe the whole thing got cooked by cosmic rays all the way through. That last possibility felt unsettling, not because it couldn't happen, but because it meant 3IATLAS had been drifting through interstellar space for an absurdly long time. We're talking hundreds of millions of years, maybe even more. Enough time for cosmic rays to work their way deep into its core. If that's true, 3IATLAS isn't just a visitor from another star. It's a relic, a frozen time capsule from the ancient galaxy, carrying clues about what things were like long before our solar system even existed. But then there was the fragmentation question. Comets fall apart. That's just what they do. They're fragile. Solar heat causes thermal stress. Uneven outgassing makes them spin and crack, and close passes by planets or the sun can tear them apart. Any of those can split a comet or break it to pieces. 3IATLAS swung into just 1.4 astronomical units from the sun at its closest. That's close enough for the sun to really cook it, heating the surface fast, causing rapid sublimation, and creating wild temperature differences between the sunlit side and the shadows. Lots of comets fragment under that kind of stress. But 3IATLAS didn't, or at least, nothing obvious. Hubble snapped some high-res images and saw no big pieces breaking off, no obvious secondary nuclei. There was maybe some dust and a few pebbles trailing behind, but nothing that screamed major breakup. So the nucleus was holding together better than expected. But why? One idea. The crust had been processed, cosmic rays baking the surface into a tough outer shell, something like ceramic that kept the inside from cracking apart. That crust might have made it more resistant to heat than regular, untouched comet ice. Another thought, maybe it just wasn't getting as much thermal stress as the models said. Maybe it reflected more sunlight than we thought, or maybe outgassing was so efficient that it vented away the heat before it could sink in and cause problems. Or maybe this nucleus was just built differently, stronger on the inside in a way our models don't capture. All of these made sense. None of them really nailed it. Meanwhile, something else was going on. After perihelion, the comet started to show a weird little acceleration that wasn't from gravity alone. Folks at JPL tracked every new position, compared the numbers, and looked for any odd shifts. What they found was strange, not because it was huge, but because it just kept happening. The acceleration didn't fade away. Normally, outgassing weakens as a comet heads away from the sun and cools down. Jets die off. The push gets weaker. The orbit should slowly return to what pure gravity predicts. But 3IATLAS kept accelerating. Just a little, steady, always in the same direction. It was tiny, just fractions of a millimeter per second squared, but it was real. And it didn't look like outgassing. Usually, outgassing causes a messy, jumpy acceleration. It flips and dips as the comet spins, as different jets switch on and off as the surface ices run out. The signal is noisy. But 3IATLAS's acceleration was smooth, almost weirdly smooth. Sure, you could say maybe the jets were perfectly balanced over the whole surface, or maybe the comet was spinning so slowly that everything evened out. But it was another thing that didn't quite fit. By mid-December, a few researchers started sharing quiet doubts, but only in private. No press releases, no big papers. Just emails between colleagues, hallway chats at conferences, whispered conversations where scientists try out ideas before putting them in print. Nobody was talking about aliens, not technology, not anything artificial. The real worry was that 3IATLAS might be something truly new, an object that didn't fit neatly as a comet or an asteroid, something shaped by processes we just didn't understand yet. Interstellar comets don't show up often. We've only nailed down 3 so far. That's just not enough to spot patterns or figure out what's normal for stuff drifting in from other star systems. Who knows? Maybe 1I/Oumuamua, 2I/Borisov, and 3IATLAS are all weird outliers. Or maybe they're typical and the models we're using are way off track. People started leaning into the cosmic ray processing idea. It made sense in some ways. Still, there were gaps. It answered a few questions and left plenty hanging. Plus, the theory depended on things like the age and backstory of 3IATLAS, and honestly, we just didn't have the right data to check those. Meanwhile, amateur shots of the comet kept spreading online. They kicked up a storm of speculation that just wouldn't quit. That blue glow, those sharp edges, a sense of structure, stuff that didn't show up in the prose images, which looked more like hazy blobs. Most scientists shrugged off these pictures as nothing but artifacts, but a handful started to wonder if there was something real hiding in the noise. Not that 3IATLAS was some alien tech, but maybe our own instruments miss details because they're built to look for certain things. Consumer telescopes, with their quirks and different software, might be catching stuff the big observatories just gloss over. That's not a crazy idea. Instrument bias is a fact of life in astronomy. Your gear shapes what you see. If your telescope is tuned for fuzzy nebulae, you might never spot anything with a crisp edge. If your detector's set up for faint, spread-out objects, it could totally miss something small and bright. But did any of that actually matter? Would those details, if they were even real, change how we saw 3IATLAS? December dragged on. The comet faded and the window to observe it kept shrinking. That big question just hung there. The data didn't want to play nice. Measurements wouldn't lock into a tidy story. Each new observation added layers, making things messier. Every bit of info tied down some things and blew open others. That's what it's like when you're staring at something totally new. You can't just drop it into your old models and expect magic. You have to start over, rethink everything, and get comfortable living with doubt. And the clock was ticking. Soon, 3IATLAS would slip away out of reach, taking its secrets with it. Section 4. The Human Edge of Cosmic Silence. There's a kind of loneliness in observation that doesn't get much airtime. Not the dreamy, old-school scene of a lone astronomer under the stars, squinting through a telescope. Everyone's seen that in movies, right? That belonged to a time when astronomy was something you could tackle alone with some patience and a decent telescope. Now, it's all about teams, remote observing from rooms that always smell faintly of electronics, working computers instead of eyepieces, data bouncing across continents in seconds. But the loneliness I'm talking about cuts deeper. It's that moment when you realize the thing you're watching out there doesn't care that you exist. It's just going about its business, following laws of physics that rolled on long before humans showed up and will keep rolling after we're gone. It would do exactly the same thing, whether or not anyone ever bothered to look. And if you miss your shot, if you don't ask the right questions, or you point the telescope a little too late, or you fumble the data before the window slams shut, the universe doesn't wait for you. The object drifts away. The chance evaporates. All you get is whatever scraps you manage to catch. Maybe that's enough, maybe it's not. Take 3IATLAS. It has no clue we're here. It doesn't know telescopes are tracking its every move, or that spectrographs are breaking down its light, or that computers are grinding away at its trajectory. It's totally oblivious to the scramble, astronomers hustling to understand it before it disappears, careers and grants on the line, entire research agendas twisting around its brief visit. All it's doing is moving. Its path is set by its own speed and the sun's gravity. Our curiosity, our confusion, our deadlines. It doesn't care. That indifference is what makes the work feel urgent. The universe runs on its own clock. It doesn't care if you're ready, or if your instrument's acting up, or if your funding about to run out. It just keeps going. By late December 2025, astronomers everywhere felt the pressure. When something rare and fleeting pops up in the data, the whole community snaps to attention. Teams across the US and the world were stitching together observing schedules, streaming data back and forth, squeezing every last drop of information out of a window that was closing fast. Up at Lowell Observatory in Flagstaff, Arizona, 210 meters high in the pine forests, astronomers were grabbing spectra every night the weather let them. The site has great seeing, dark and steady enough for really precise observations. Still, nothing could change the fact that 3IATLAS was fading night by night. The focus was on the coma, tracking how its makeup shifted as the object moved away from the sun. Each spectrum split the comet's light into its colors, mapping out the unique lines from water vapor, carbon dioxide, carbon monoxide, methane, ammonia. Each molecule leaves its own mark. With spectra taken weeks apart, you could actually watch the chemistry change as the comet cooled, different ices evaporating at their own rates. The hope was to catch new material getting exposed, maybe some untouched ice from deep inside, stuff that hadn't seen cosmic rays during its time between the stars. But the data just sat there, stubborn and steady. The gas ratios weren't shifting like the models said they should. Carbon dioxide kept dominating. It started to look like the whole object, not just the surface, had been processed evenly. Or maybe the sublimation was stuck in some kind of steady mode, not reacting to distance or sunlight the way everyone expected. Meanwhile, over at McDonald Observatory in the Davis Mountains of West Texas, another place with a long astronomy pedigree, researchers were almost obsessed with polarimetry. That weird negative polarization branch spotted earlier needed constant monitoring. Would it stick around, or finally budge as the comet's activity faded and the viewing angle changed? Nobody wanted to miss it. Polarimetry sounds like one of those obscure techniques, but honestly it gives you some of the most important clues. When light bounces off particles, it gets partially polarized. The waves don't just vibrate in every direction anymore, they pick favorites. The way that light lines up depends on what it hits. The size, shape, and makeup of the particles matter. With comets, polarimetry basically lets you peek at the dust in the coma. Are the grains tiny or chunky? Do they have jagged edges or are they smooth? Are they made from organic silicates or something stranger? Each mix leaves its own distinct fingerprint in the polarization. Then came 3IATLAS. Its polarization signature just didn't fit anything anyone had seen before. What's more, it refused to budge. Night after night, researchers measured polarization from every possible angle between the Sun, the comet, and Earth. No matter what, the signature stayed weird. The negative branch stayed deep. The inversion angle stayed tight. Whatever was scattering the light, it wasn't behaving the way comet dust normally does. That stubbornness pointed to something fundamental about this object. What exactly? No one could say. And that was infuriating. Meanwhile, over at NASA's Jet Propulsion Laboratory in Pasadena, the orbital dynamics team was working overtime. They updated trajectory calculations every day, folding in every fresh position measurement to pin down the comet's non-gravitational acceleration. They built models for jet locations and directions, and tried to estimate how much mass those jets were blasting out. Hubble, managed by NASA and the Space Telescope Science Institute in Baltimore, kept snapping images of 3IATLAS. Every set got the full treatment, searching for fragments, changes in the coma, any sign of structure that might explain what was happening. The James Webb Space Telescope came in with follow-up infrared spectra, hopping to catch molecules that earlier observations missed. Webb can pick up incredibly faint emission lines, and scientists were desperate for any trace gases that could offer clues about where this comet came from. But time was running out. 3IATLAS was past 2 astronomical units from the Sun now, speeding away at several kilometers per second. Its light was fading fast. Smaller telescopes had already lost it. Even mid-sized ones were struggling to see anything at all. Only the biggest ground-based telescopes and a few space observatories could still collect real data, and even they were having trouble. Ask around, and you get a different answer about how much longer 3IATLAS would be visible. Some thought there was time until mid-January 2026. Others were less optimistic. They figured high-quality data would be out of reach by the end of December 2025. Back in early December, the best guess was 47 days. Now, with December winding down, that window had shrunk. Maybe 3 weeks left, maybe less. And the tension was rising. There's a special kind of pressure that comes with studying something fleeting. This isn't lab science where you can just try again if something fails. It's not theory where you can come back to a problem whenever you want. Here, you get one shot. It's all about timing and luck, and the universe doesn't care about your schedule. Miss a crucial observation because of clouds, a scheduling mix-up, or just not thinking to look until too late. That data, gone forever. The comet moves on, the scene changes. The chance disappears. Everyone working on 3IATLAS felt that. Every clear night mattered. Every photon was a win. And every cloudy night, every glitch, every frustrating pause felt like a gut punch. On top of that, there was this bigger emotional backdrop. For a lot of the team, especially the younger researchers, this was their first shot at studying something from another star. 1/Oumuamua had zipped past before most grad students could even jump in. 2/Borisov stuck around longer, but it played by the rules. It didn't throw out the kind of puzzles 3IATLAS was throwing out now. Something felt different this time. This wasn't just another observation campaign. It had that electric charge, the sense that people would look back on this moment for years. Careers would be defined by what happened here. Textbooks would mention it, but only if they could actually figure out what the hell they were looking at. The problem wasn't just technical. It was deeper than that, conceptual. The data coming in from 3IATLAS just didn't slot into any of the usual categories. Sure, the comet model explained a lot, but not everything. The cosmic ray processing idea patched a few holes but left too many open, and every new batch of data seemed to make things messier. That's just science, honestly. Progress isn't clean. You run into something weird, you try to build new ideas around it, you throw those against the wall and see if they stick. Eventually, you hope you land on an explanation that actually works. Still, that doesn't make it less frustrating. Especially when the clock's ticking and you know your window won't stay open forever. There were these moments, late at night, in control rooms lit by monitors and coffee machines, where researchers stared at the latest images and felt this gnawing uncertainty. Not about the measurements, those were solid, but about what the numbers were telling them. Was 3IATLAS just some freak comet? A statistical outlier, strange but not rewriting the rules. Or was it showing us something bigger, something we'd never seen before in the whole universe of interstellar objects? The cosmic ray processing theory made sense on paper. It covered a lot of ground, but everyone knew it was a bit of a stand-in, just holding the spot until something more convincing turned up. And then there were those stubborn little details that wouldn't fall in line. The odd acceleration, the brightness that didn't add up, the way it held together, the weird polarization. None of them were impossible to explain on their own, but together they formed this nagging sense that the picture was just off. Not a dramatic wrongness, but the kind that sticks in your head and keeps you up at night because it means your model isn't quite right. One researcher at Lowell Observatory put it perfectly in an email. Every time we think we've got it, the data does something just a bit off. It's like tuning a radio that's almost on the station, but there's still static. You can hear the music, but you can't tell if the static is just noise or if it's part of the song. That same uncertainty spilled over into the amateur community. People like Paul Craigs were posting images from their backyards, and nobody could quite agree on what they were seeing. Some pros tried to copy the images with similar gear and methods. A few pulled it off. They got the sharp edges, the blue glow, but there was no consensus about what any of it meant. Most astronomers chalked it up to processing glitches, nothing more. But the door stayed open just a crack. A few researchers started to wonder, maybe the amateurs were actually picking up something real. Not proof of anything artificial or wild, just the object's weird surface scattering light in unexpected ways. It was just another idea. They'd need more data to know if it was anything at all. Meanwhile, out in the world, the story of 3IATLAS was catching fire in ways nobody expected. Science communicators, space nerds, random people scrolling through forums, everyone had an opinion. Some of it was grounded in real science, but plenty of it veered off into strange territory, the kind that made actual astronomers grit their teeth. The big challenge for the scientists was figuring out how to talk about what they didn't know, without accidentally lighting a fuse under the conspiracy crowd. How do you say, "We don't know yet," without people hearing, "They're hiding something"? NASA played it safe and steady. Their statements stuck to the script. All signs point to 3IATLAS being a natural comet. They admitted the weird bits, the polarization, the CO2, all that, but called them puzzles, not deep mysteries. But behind closed doors, people were more honest about the confusion. At conferences, in peer reviews, in grant pitches, researchers didn't hold back. 3IATLAS was shaking up old ideas, forcing them to rethink what they thought they knew about stuff from outside our solar system. And nobody was pretending otherwise. This is what science really looks like. Out in public, everything sounds careful and tidy because people want answers that feel solid. But behind the scenes, it's a mess. False starts, arguments, half-formed ideas that never quite settled down. That's exactly what 3IATLAS left behind as it faded from sight. A tangled pile of observations, questions stacked on questions, the kind of puzzle that takes years to pick apart and make sense of. By late December, reality was sinking in. The window to watch this thing was closing fast. Bad weather knocked out several important observatories. Equipment issues cost precious nights, and the comet itself was dimming quicker than some folks had expected. 47 nights to observe turned into 30, then 20. Then, as January 2026 showed up, maybe less than 2 weeks were left. That was it. You could feel the pressure. This was the last shot to grab the data that might finally explain what was going on, or at least help narrow down the options. People scrambled to write proposals for future studies, hopping to squeeze more from old data. Teams started planning how to wring every last bit of value out of the images and spectra they'd managed to collect. There was talk about bringing in machine learning, letting algorithms hunt for patterns that humans might miss. But honestly, everyone knew the real action was happening right then, in those final nights before 3IATLAS vanished from our reach. During those nights, something changed. The focus in the observatories felt almost sacred, not because the comet was holy, but because the chance to witness it was disappearing. The universe had tossed a gift our way, and now it was being pulled back. Astronomers are used to this. Their work stretches across timescales that make a human life look tiny. Sometimes they catch light that's set out long before people even existed. Most of their questions, they know they probably won't get answers within their own lifetimes. But sometimes, just sometimes, something shows up that's close, right here, right now. When that happens, you pay attention. You dig in. You deal with the uncertainty, the frustration, the reality that you probably won't solve at all. Because letting it slip by unseen, unstudied, that's just not an option. 3IATLAS was disappearing. But nobody was looking away. Section 5. What remains when the light fades? Astronomy doesn't usually tie things up with a neat little bow. People imagine scientists wrapping up mysteries with a flourish, data fits, models work, the paper's done, mystery solved. Sure, that happens, just not as often as you'd think. More often, things end in a quieter, messier way. The object you're watching fades. The numbers stop coming. You walk away with a little more knowledge than you started with, but a lot less certainty than you'd hoped for. You've learned something real, something that matters, but you're so aware of everything you missed, every question you couldn't answer, every measurement you never got to make, every mystery that just slipped away. That's where we are now with 3IATLAS. There's no satisfying conclusion here, no final definite answers. What we get is something else, maybe something more honest about how science really works, especially when you're up against stuff that just doesn't fit the rules we thought we had. 3IATLAS is literally fading away. Its brightness, that apparent magnitude astronomers talk about, keeps dropping as it drifts farther from the sun and farther from us, back into the darkness it came from. Each night, it's harder to spot. You need longer exposures just to scrape together enough light for a decent look. The signal-to-noise ratio, the line between getting something real and just picking up static, keeps dropping, no matter what you do. Pretty soon, maybe in a few days, maybe a couple weeks if you've got a sensitive telescope, 3IATLAS will slip below the limit. All you'll see on the detector is background noise. That random static that's always there, swamping any faint signal that's left. The spectrum will get too weak to pull anything out, no more clear emission lines, just noise. Pinpointing its position, refining the orbit becomes a guessing game when the signal's this faint. And when that line gets crossed, the observing ends. Not because the object is gone, it's still out there, moving through space, keeping its secrets. But we can't see it anymore. There's nothing left to measure, nothing left to learn. That's it. The window closes. What we've gathered, the data, the ideas, the scraps of understanding, that's all we get. No do-overs. No going back for the shot you missed or the question you didn't think to ask until it was already too late. That's the reality for everyone working on 3IATLAS right now. The last images are getting snapped. The final spectra are coming in. The last bits of data are being logged. Very soon, all the frantic work of collecting data will stop and the real work, slow, careful analysis takes over. We'll go from asking what are we seeing to what did we see? That shift from present to past has a kind of sadness to it. The thing itself, the living, moving event, is gone. All that's left are echoes. The light it sent, the tiny tug it gave the planets, frozen there in the numbers. And the big question, what is 3IATLAS really, still hangs in the air. We do have answers, or at least our best guesses, built from the evidence we managed to collect and the models we can build. But those answers come with asterisks, with gaps we just can't fill, with uncertainty we can't shake. And with no more data coming, those gaps are here to stay. Most scientists who have looked at 3IATLAS and written about it agree. It's an interstellar comet. Picture a chunk of ice and rock that formed around some distant star billions of years ago, then got tossed out into deep space, probably when the planets in its home system were still sorting themselves out and flinging things around. After wandering through the galaxy for who knows how long, it finally swung close enough to our sun that the heat woke it up, lighting up a coma and tail that made it stand out. Now about those weird details. Like all that carbon dioxide instead of water, the strange way it polarized light, its steady acceleration, the brightness that didn't quite fit, even how tough it seemed. Scientists usually chalk all of that up to cosmic ray processing. Basically, the idea is that after millions or billions of years drifting between stars, High-energy particles bombarded its surface, changing its chemistry and texture in ways we just don't see with comets from our own solar system. Still, some things don't line up perfectly. The steady, non-gravitational acceleration, smooth, consistent, and lasting for weeks, sort of fits what you'd expect from outgassing, but the data looks cleaner than usual. Then there's the brightness bump that started in November and just kept going. The models said it should be dimmer, and the spectrum never showed anything that would explain why it was shining extra bright. And somehow, even after swinging so close to the sun, 3IATLAS didn't break apart. No fragments, nothing. That hints at a nucleus that's either super strong or strangely unified. Maybe that's another side effect of its cosmic ray crust. Maybe, but nobody can say for sure. And let's not forget the amateur images. Some show odd structures that don't match what the pros see. Most researchers figure those are just artifacts, overprocessed data, noise that our brains can't help but turn into patterns. But if you talk to a few scientists off the record, some admit there's a sliver of doubt. Maybe there's something about the surface or the coma that, under the right conditions, creates the illusion of structure. Not because the comet's artificial, but because the mix of cosmic ray damage, sublimation, and light scattering is doing something we haven't fully figured out yet. It's a tiny crack in the certainty, just a faint, nagging question in the back of the mind. But it's there. The bigger picture, 3IATLAS has shaken things up. We don't have all the answers, but it's made researchers rethink what they thought they knew about interstellar objects, about how cosmic rays can change a comet, about what comets can even be like when they come from such extreme environments. It's another reminder of how much we still don't know about our own galaxy. In less than 10 years, we've found 3 interstellar visitors. That's hardly enough to draw big conclusions. Maybe they're typical. Maybe they're weird exceptions. Maybe the next one will be totally different. That kind of uncertainty can feel uncomfortable, but it matters. It keeps us honest. It reminds us the universe is wilder and more complicated than whatever models we've built so far. There are things out there we haven't even imagined. Every time we spot something new, there's a real chance it'll flip our understanding on its head. Scientists will be picking apart the data from 3IATLAS for years, maybe decades. That's just how astronomy goes. The actual observing is a rush, but it's over fast. Afterward, people spend ages combing through the data, squeezing out insights, building new models, and writing paper after paper. You can bet research teams will focus on every angle. Some will dive deep into spectroscopy, cataloging every molecule and tracking how things changed over time. Others will dig into photometry and polarimetry, trying to pin down what the dust is like and how the coma is structured. And there'll be folks working on the orbit, running models to figure out what that steady acceleration says about the comet's shape, spin, and how it's venting gas. That's how it goes. One strange visitor and suddenly everyone's got new questions. And that's a good thing. The models aren't set in stone. They'll keep evolving. Each new batch of data will push scientists to tweak the cosmic ray processing theory, or maybe even come up with a whole new idea for why these weird features show up. People will run more lab experiments, blasting different ice mixtures with radiation to see which ones end up looking like what we saw. And then there's the computer side. Simulations will map out how an interstellar object might react to sunlight, depending on what it's made of inside. Some things will get sorted out for good. The gases in the coma, scientists will pin down exactly what's in there. They'll nail the ratio of carbon dioxide to water, no problem. They'll also be able to rewind the object's path through space, so we'll have a pretty good guess where 3IATLAS came from and how it was moving before it wandered into our solar system. But not everything will get a neat ending. The nucleus size. We'll get a tighter estimate, maybe down to a factor of 2 or 3 instead of 10. But unless someone figures out a clever new trick to separate the nucleus's light from the coma in old images, we won't get an exact measurement. What about the inside? Solid chunk, pile of rubble, or something else? Without seismic data, which we definitely don't have, it'll stay a mystery. And then there are the questions that just hang out there, probably forever. We won't know how old 3IATLAS is, or how long it drifted through the void before showing up here. Sure, people will make guesses based on how much radiation it's soaked up, but those guesses depend on a whole bunch of assumptions about the galaxy and its path, assumptions nobody can really check. We'll never know what star system it came from either. You can only trace its path back so far before all the uncertainties pile up, and then suddenly you're looking at millions of possible origin stars. It could be from just about anywhere in that patch of the sky, and we've got no way to narrow it down. What's inside under that weathered crust? Is there untouched ice, still holding secrets from its birth? Or did radiation work its way right through, changing everything? Unless someone drills into it or it breaks apart in front of us, we'll always be guessing. And unless a bunch more interstellar visitors show up looking similar, we can't say if 3IATLAS is just a weird one-off or a pretty standard example. 3 objects, Oumuamua and Borisov and this one, aren't enough to know what normal even means for these things. For all we know, they're all outliers. Or maybe they each belong to a totally different group. We need to spot dozens, maybe hundreds, before we can start talking about statistics. But honestly, that's just how science goes. You very rarely tie up every loose end. You chip away at the unknowns. You toss out some theories and shore up others. You set the stage for the next round of discoveries and the next set of questions. In the end, most folks in the field will probably agree. The cosmic ray processing story makes sense. An interstellar comet born around another star, flung out young, battered by radiation as it wandered the galaxy and finally spotted by us in the tiny window when it zipped through the solar system. The weird stuff, what sets it apart from local comets, fits pretty well with that journey. No need for wild new physics or exotic explanations. That's enough for most researchers and for most people following along. It fits the facts. It works with what we already know about the universe. For almost everyone, that's where the story ends. 3IATLAS gets tucked away as an interesting case, a successful observation, a cool example of scientists around the world pulling together fast. A decade from now, maybe it gets a short mention in textbooks, the third interstellar object we caught, known for its high carbon dioxide to water ratio and clear signs of long-term cosmic ray processing. A few researchers just can't shake this feeling, this quiet, persistent doubt that lingers in the background. It's not about aliens or secret artificial origins. The numbers don't point that way. It's more about whether we've really wrapped our heads around what we're seeing. Does the cosmic ray processing theory cover everything, or just most things? Are there pieces we're missing simply because we haven't come up with the right ideas to even notice them? Take that steady, non-gravitational acceleration. It didn't act like you'd expect if outgassing were behind it. The push was smooth, not erratic. Maybe that's telling us something and we're just not listening. Or the brightness that popped up after perihelion and stuck around. What if that's a clue to a process we don't get yet? And the way the thing held together, even under intense heat, no sign of breaking apart. Maybe that says something fundamental about how stuff survives between the stars that our models just don't capture. This isn't wild speculation. These are the questions that haunt careful scientists late at night, staring at data that almost fits but not quite. When your model explains 90% of the puzzle but that stubborn 10% just won't slot in, you have to wonder, is that just noise, fluke readings, ordinary wiggle room? Or is it the universe trying to nudge you towards something deeper? With 3IATLAS, we might never get a final answer. The data is what it is. The window's closing. Now we're left with a picture that's almost finished, but not entirely, like a jigsaw puzzle missing a handful of pieces. You know what the image is, but those empty spots leave some details out of reach. Maybe that's just how it goes. The universe doesn't promise us tidy solutions. It doesn't owe us full explanations or wrapped-up mysteries. It throws phenomena our way, and we do what we can, working with the time and tools we have. 3IATLAS came from somewhere we'll never see, a star system that's probably gone now, disrupted or swallowed up ages ago. It wandered through the galaxy for who knows how long, facing conditions we can barely imagine, let alone recreate. Then, just by chance, it crossed paths with our solar system during the brief moment humans had the gear to spot and study something like this. Honestly, we were lucky to see it at all. We learned from it, and we're still learning. The data it gave us will shape how we think about interstellar objects, cosmic ray processing, comet physics. This stuff will echo through the field for decades. Next time an interstellar visitor shows up, whenever that is, we'll use what 3IATLAS taught us. We'll be a bit more ready. Maybe we won't be caught so off guard. We'll know what questions to ask while we have the chance. But let's be real, we'll probably still be surprised. That's how the universe keeps us honest. Just when you think you've got things figured out, it throws you a curveball, a detail that doesn't fit, a reminder that there's more work to do. 3IATLAS is fading now. The light's almost gone. The stream of data is drying up. The observation phase is ending, and soon all we'll have is what we captured. Those photons, those notes, those numbers. The questions will stick around, though. Some will get answers as we dig into the data and sharpen our models. Some will get narrowed down. And some will just hang there, waiting for the next visitor, the next shot at testing our ideas against reality. And out there somewhere in the dark between the stars, the next messenger is already on its way. Moving fast through the void, set on a path by long-ago gravitational encounters, totally unaware that ahead, on a small planet circling an ordinary star, there are curious beings with telescopes, waiting for whatever comes next. We don't know it yet, but we will. When that next interstellar object enters our skis and starts showing up in survey images, we'll jump into action, just like before. We'll coordinate, scramble, and try to make sense of it before it slips away again. Next time around, we'll have sharper tools, smarter models. We'll ask better questions, too. Maybe we'll spot what slipped by us with 3IATLAS. Or who knows, we might bump into something completely new, fresh mysteries, strange anomalies that push us in directions we never expected. Whatever happens, we'll show up. We'll keep watching, keep measuring, keep trying to make sense of it all. That's just what we do. When people meet the unknown, we don't back off. We grab a telescope, catch whatever light we can, and start asking, what are you? Where did you come from? What secrets do you hold about the universe outside our tiny patch of sky? 3IATLAS didn't hand us every answer. It gave us a few, sure, but it left us with even more questions. And in the end, that's the real lesson. The universe is massive, bizarre, and packed with wonders we're just starting to notice, let alone understand. Now the light from 3IATLAS is slipping away, but those questions, they're still here, and maybe that's exactly how it's supposed to be.